Hey, Andrew McLaren. So we're going to talk about empirical formulas and molecular formulas and how you solve problems involving those, as well as really trying to identify these things and think about what they mean. So we're going to spend a fair amount of time looking at the main idea about empirical formulas and molecular formulas. They're sometimes written as EF and MF. You might see me abbreviate that a few times in this lesson. We're going to really also be trying to think about what this means in terms of the atoms in one molecule, and if you can conceptually think about what a molecule is, that'll be very helpful for this lesson. I do have a whole video on chemical formulas and drawing out one molecule or drawing out two molecules of the same compound. I'll briefly go over that today, but that's going to be critical for thinking about like why we're using moles instead of grams to find like the empirical formula. So I'm going to try and help you have some self checks throughout these problems to think how the concepts link to the math. We'll do that with a couple like typical high school problems, and we'll also do that with a challenge problem that's like from a college level chemistry class. Okay. When tutoring students on empirical formulas and molecular formulas, I just ask them to define these two. And what's really interesting is they don't really know what the words mean. They just say, oh, you need to multiply one to get the other. And you can't think through this like that. You can't be thinking like, oh, I'm just multiplying one to get the other one. That's, yes, that is the math, but you really can't be thinking about that in terms of what these words mean, because it's going to really mess you up. So we have to think about empirical in terms of not like, oh, I need to multiply, or molecular in terms of like, oh, I need to multiply or divide to get the other number. What we need to really think about is what these numbers really mean. The empirical, this is the ratio, and this would be like smallest whole numbers of the atoms. And the molecular, this is the number of atoms in one molecule. So this might be something like C2H4, right? And then the empirical formula for that would be CH2, which is really, honestly, it's kind of weird that they even write empirical formulas out like this, because this is really just saying that you've got one C to every two H. Okay, and we're talking about atoms, like one carbon atom for every two hydrogen atoms. So when we're talking about empirical formula, this is really talking about the ratio of atoms. And it also helps to know like what empirical means and what molecular means. Molecular has to do with molecule. That kind of makes sense. Empirical, this means from a lab or from observations. So when we're talking about something being empirical, like empirical evidence, that's something that's from a lab, or empirical data, that's these are observations and things that we can get data on and share. So typically when we're talking about scientific data, we're talking about things that are empirical, right? And so that helps me remember what these things are. And so what we have is we have the empirical, which gives us the ratio. Like you're going to be able to say how much carbon and hydrogen there is after you've done a lab. But you would actually have to know the molar mass to turn that into the molecular. So the thing that people typically think about with these things is like, oh, I need to multiply to get this. So you multiply by the molar mass, or not by the molar mass, sorry. No, you multiply by to get the molecular formula, and then you can say that's going to be correlated to the molar mass. So like these things are related. So if you have like a really big molecule, it's got a ton of atoms in it, the molar mass is going to be really heavy, right? So you can look at the molar mass, and that's going to be related to the molecular formula. The empirical formula is just the ratio between these things. So if I wanted to draw out a couple different chemicals and look at their empirical formulas versus their um, their molecular, so we could do empirical formulas. We'll do that in purple, and we'll do in green. We'll do our molecular formulas. So if we have the chemical, let's say that we've got this chemical right here. So if you're not sure how to draw out chemicals, that is something that I do have a whole video on. But let's say that we have this chemical right here. This is C2H4. I think it's ethylene, I believe is the name of it. So the empirical formula for this guy is just CH2 because that's the ratio between these. There's one of these to every two of those. There was 2 to 4 in the ratio. So that's the empirical formula. So we'll do that in purple. This thing's molecular formula, on the other hand, is going to be C2H4. And so this one chemical, it's got these two different things that you can write about it, the empirical formula, that molecular formula. And then we can also look at this thing's molar mass. I'm going to just do an estimate for its molar mass because carbon's about 12, hydrogen's about 1. That's like 14 per. This is actually like 28 grams per mole. Because these are 12 each, that's 24, plus another 4, that's like 28. So this chemical has a molar mass, and that molar mass correlates to the molecular formula, like molar, molecular, right? All is related there. It's through relating that one molecule and thinking about that one molecule. So if we look at this idea, it's really important to think that this is the number of atoms. And these are a number of atoms, and these are like the ratio of the atoms. And the idea behind this is that this chemical, sure, there's twice as many hydrogen as there are carbons, but you don't have twice as many grams of hydrogen as there are of carbon. In this situation, we can say that there was either 12 grams carbon to 2 grams hydrogen, or if we're looking at the molecular formula, this was 24 grams carbon to 4 grams hydrogen. So we don't typically write these out with grams. We write them out as molecules because this is one atom of carbon and 2 atoms of hydrogen. You could also think of this as 1 mole of carbon and 2 moles of hydrogen. Like because we can say this is the ratio of atoms, we can also talk about it as moles. Because remember, moles is just a giant number of molecules or atoms in this case. You can just say like, oh, instead of looking at these individual atoms, we're looking at like the big number of them. So we're talking about a bigger scale thing. But the atoms and molecules, that's the ratio, really. It's not having to do with grams, it's having to do with the molecules there. And if you can conceptually think about that, that will make these problems a lot easier. Okay, so let's look at a couple other chemicals. So let's say we've got the chemical N4O6. This chemical, I might need to double check what it looks like, to be honest. Yeah, just give me a second. We gotta double check that. Okay, so this is an actual chemical. The other one that we were doing earlier was not. This chemical, we can look at it like we did with the last one and say, what are my empirical and molecular formulas? And basically, what we can say for this one is that it's got a ratio of, it looks like 1 nitrogen for every 2 oxygens, but the actual molecule has 2 nitrogens in it and 4 oxygens. And this is just an important thing to note, that when we write something like 2NO2, this is not the same as N2O4, because in this situation, this is like something that looks like this. I think it's something like that. And there's two of these, right? So that's kind of like what this is. And then this is more of like what we were originally talking about over here. Like these things are not exactly equal. And they do have the same amount of atoms, like the atoms. Sure, that's equal between these two things, like the number of atoms. But how they're packaged, the molecules, very different. Those are not the same molecule. They're gonna have different properties. Like these things, because they're smaller, are gonna boil off sooner. Like they've got different boiling points and everything. So this is not the same as that. This is, in this case, I've drawn two molecules of NO2 and one molecule of N2O4. That was honestly just to demonstrate the difference between the two. We're not really looking at NO2 right now, right? We were looking at this chemical. And when we're drawing this chemical, its empirical formula is NO2. You can also consider the NO2, that chemical, right? And so we can say, okay, I have this chemical. Um, and again, I think it looks something like this. I could be getting the electrons wrong. I think one of these might be double bonded on there. In any case, this is kind of what it looks like. And we're going to have the empirical formula for this is NO2, and the molecular formula also is NO2. In this case, the empirical formula is the same as the molecular formula. Just sometimes the most simple ratio between the atoms is what actually is in the molecule. That does occasionally happen. So that's kind of what's going on here, and how you can think about how those are similar and different. And then I want to also do glucose, yeah, and talk about that one. So if we're talking about uh, C6H12O6, that chemical, that would be like glucose. And so it's, when we're talking about that, sorry, just trying to keep these here. So if we're talking about this, the empirical formula for this guy is going to be C1H2O1, and we typically don't write the ones in here. That's just a convention of how we, when we're writing out atoms in a molecule or empirical formula. If it's two, you include it, or three, you include it, but if it's one, you don't have to. Okay, and then the molecular formula for this would be C6H12O6. This is showing the actual things in the molecule, whereas this is just showing the ratio between them, right? Now I need to actually Google glucose to draw it out. Give me a second. Okay, I believe that is glucose drawn out. It's a pretty big chemical, as you can see. There's a lot of carbons, hydrogens, and oxygens. But if you have a 6 carbons and 6 oxygens, they have a 1-to-1 ratio. So that's why this empirical formula is 1-to-1. And if you draw this guy out, this is that chemical. It's showing the number of atoms in the molecular formula in one of these. So if we also were to consider drawing out, there's a couple other things you can do that have the same ratio. There's also like, we could actually draw out the chemical CH2O and look at what that looks like. I believe this is something like so, is what that would actually look like. And if we're talking about its empirical formula, it's the same as its molecular formula. Because you can't simplify the numbers down to any more simple whole numbers, you just write the empirical formula the same as you would write the molecular formula for these guys. There is, I think, also, I want to say, hold on. I think that this is also a chemical. Isn't that carboxyl? I think that might be this guy right here. Yep. That's just a chemical that you'll be familiar with if you've done OChem. So That's what that kind of looks like if you were to actually draw out the structure. And then again, we have its empirical formula. If we were to simplify the ratio, is the same as what we've been looking at before. But now this, its molecule is, there's actually two carbons, right? And there's actually four hydrogens, and we can see that. And there's actually two oxygens, okay? So you may not be like able to draw these formulas out reliably, probably can't, but you can conceptually think about the main idea is that the number of these things in one molecule relates to the molecular formula, and the empirical formula is just reduced to the smallest whole numbers. Sometimes when the molecules are very small, the empirical formula is the same as the molecular formula. That's the main idea on these, at least how I like to think about them. When this concept is introduced, either high school or college chemistry, they usually start you off with one of these two parts. Part one being where you're given either grams or percentages, and you have to get the empirical formula, or part two where you know what the empirical formula is and the molar mass. You're either given that or you're able to figure it out, and you need to use those two pieces of information to find the molecular formula. So there's kind of two parts to this that you'll typically see, and then a lot of times they'll put them together into like a big problem, and that'll be kind of like what we're seeing by the end of this. So if I had some chemical that I knew that had carbon and hydrogen in it, and they've given me these two amounts of grams, what we want is we want to know the amount of moles of carbon compared to the amount of moles of hydrogen. And remember, we're doing like these numbers are the atoms. And so that correlates to moles. And so if we have grams, we have to turn them first into moles. So we have the 4.5 grams of carbon, and then you need to multiply that by its molar mass. In 1 mole, there's, I think it's 12.01 grams of carbon, and then we can figure out that as moles. We can do the same thing with hydrogen. So in this case, we're just using a single hydrogen atom. And so its molar mass is like 1.08, I think, or 1.008, I want to say. And that's for every mole of hydrogen. And so we can see right here, we actually have, what is this? 4.5 by. And if your molar masses are slightly off, it actually doesn't really affect these problems typically, as long as like, because you're going to end up estimating when you're doing these numbers ultimately anyways. So it kind of is okay if it's not the exact number here, because you're going to end up rounding later anyways. So we've got that amount of carbon, and then if we take our 1.5 and divide it by 1.008, it's basically 1.5. Okay, so we've got 1.48806, I think. Yeah, and there is some stuff where or oh 09. You do have to be kind of careful with some of these numbers because there's some situations where you can be close, but it's not quite right. So we have, and that's moles of H as well. So we have a certain number of moles and another number of moles, and we want to know what the ratio is between those two things. So we had, in this problem, we want to know the empirical formula. We need to know what these numbers are in here, the whole numbers, because ultimately we're going to end up having whole numbers here, right? So this needs to be whole numbers. So if we think about just these as the numbers that they've given us, we've got 0.3746 moles of carbon, and that is related to the 1.4 moles of hydrogen. So I'm just going to copy that over. So if I want to make these whole numbers, I need to divide by the smallest number that we're seeing. And that will make it a whole number, right? Any number divided by itself will give you 1. So we want to make the smallest number 1, and in this case it was nice and easy, so we were able to get 1 carbon, 1 molecule of carbon, or 1 mole of carbon for every, it looks to me like this is going to be 4. Let's divide this by, yep, this is 3.97 moles H. We're going to round that and say that it's 4. And so in this situation, we can say that there's 4 hydrogen molecules or moles of this for every carbon mole of carbon. So there's 4 atoms of hydrogen for every 1 atom of carbon. And so this has an empirical formula of CH4. Now, they haven't given us the molar mass at this point, so we can't really say that that's also the molecular formula, but we can definitely say that this is the empirical. If they had given us the molar mass, then we'd be able to determine the molecular formula by multiplying this by whatever we need to get that total mass. Because if you look at this thing, this molar mass is like 12 plus another 4, so it's like 16. So if we have a molar mass of 16, then this is actually our chemical. But if it was 32, then we would need to double up our numbers in here, and it'd be C2H8, right? Okay. I think I might have moved things and then it messed up. Yeah. Kind of messed up our stuff there when I moved some of my problems around. Okay, so if we look at a different scenario, let's say that we're trying to use the find the molecular formula. So let's say that you have a chemical and there's 2 nitrogens for every 3 oxygens. So 2N to every 3 O, and these are atoms. Okay. And so we can write that out if we want to say it's empirical formula. We would write that out as N2O3. But if we look at this, we now know the molar mass is 76 grams per mole. And if I looked at this formula, this is basically 2 times 14 plus 3 times 16. I'm just looking at that. It's going to be what, like, I think that might actually get us close. Let's just double check it. Yeah, if we actually get the calculator out here, this is 28 plus 46. Yep, this is 76 for our grams per mole. So this not only is the empirical formula, but it's actually the molecular formula. So we can say the molecular formula for this is actually going to be N2O3, because we can see when we add up the things, it gives us the right molar mass. So our molecular formula in this case is the empirical formula. That does occasionally happen. Now, if we had a slightly different problem, oh man, this is getting all kinds of messed up. Give me a second. Okay, that's better. So if we have another chemical where we've got 1 carbon, so it's just 1 carbon for every 2 hydrogen and 1 oxygen, and these are atoms. We can write that out. It's empirical formula. It's going to be CH2O. And then we can look at its molar mass. Its molar mass is equal to 180 grams per mole. And what we can do is we can say, well, how much would this weigh, the empirical formula? And it looks to me like this is what, 12 plus 2 times 1 plus 16. I'm just going to estimate just because we'll be able to do a little bit of estimation. You got to be careful about doing too much on some problems, but in general, this is okay. So what is this, 30? This is 30 grams per mole for its mass, right? And so it looks to me like if we had one carbon, two hydrogens, and oxygen, that'd be 30, but we would need it to be 180 grams per mole. So we're going to need to multiply that by, what is that? 6? Yeah. So that multiplies this by 6. So what we need to do is we need to take our empirical formula and also multiply that by 6 because this weighed 30 grams per mole, and that then this was 180 grams per mole, and this is that molecular formula, right? So if we have 6 times CH2O, that's the same as saying something like this. So in each one of these molecules, this is that glucose molecule we were looking at earlier. There's 6 carbons, 12 hydrogens, and 6 oxygens. The ratio of this is 1 to 2 to 1. But because we know the molar mass is 180, we can say this is our molecular formula for this chemical. So they'll oftentimes give you something like that, right? Now, the interesting thing is they really like to kind of bring both of these parts together, where you have like this molecular empirical formula, and you're trying to find both of them, and they might just give you like the percentages here. So you gotta be a little bit careful with these ones. Okay, and also I just want to talk a little bit about when they give you percentages right here. You can set your sample to be 100 grams, and then 36.8%, that is going to be 36.8 grams. And so when we typically think of these problems as having 100 grams when they give us percentages, and then that just makes it really easy to work with, right? Because then we can just consider that point in time and look at those moles, and then we can apply that to situations where maybe you don't have a 100-gram sample. Maybe it's 20 grams of the sample or something, but you still have the same chemical. And so this is the grams of oxygen in this case. Okay. And so it's very much like the other parts. Now that we have grams, we need to turn it into moles and atoms, and that will then be allowing us to do empirical formulas. So that's kind of important. And then once we have the empirical formula, we should be able to find the molecular formula. So if we look at this, we've got the 63.2 grams of oxygen. Let's just say 16 grams per mole oxygen. We can find that. And 36.8 grams of nitrogen. Let's find out how many moles that is. Yeah, it's kind of interesting because you'll kind of get a sense of these numbers and their molar masses, and you'll kind of be able to see which one. When they give you these percentages, you'll be like, oh, that's, not that much of this chemical or a whole lot of that in terms of its moles. Nitrogen, is that 14? I believe it's 14. Looking at nitrogens, yeah, it's 14.007. We're just gonna go with 14. Just, it'll be fine for this big picture calculation. 63.2 divided by 16. We got 3.95 moles of oxygen, and then we've got looks like about a little bit more than 2. 8 divided by 14, and we get 2.62 85 moles of nitrogen. So if we're just looking at these things um, it's not going to be a whole number, I don't think. So if we look at, yeah, because this and that, it's like 4 and 2.5. So these are not going to work out perfectly, but we should be able to get close to a whole number with this. So if we wanted to get our moles of N to our moles of O, we've got that ratio we can think of as the 2.6285, and this is the 3.95. We need to turn these into whole numbers. So if we look at this and that, if we divide them both by the 2.6285, let's see what we get there. 2. Hold on. 3.95 divided by 2.6285. Yep. Nope. That was weird. We did something weird on math. Okay, there we go. That is more accurate. So if we do this, we get a 1 to like 1.5 ratio. We can't have a 1.5 ratio. If you're close to half, you're probably gonna have to double it. So to make these nice even whole numbers, we're gonna do 2 moles of nitrogen to 3 moles of oxygen. So just be careful here. If when you're simplifying, you get close to like a 0.5 or a 0.3, you might need to multiply to get whole numbers. Unfortunately, this is just, you gotta have to get a sense of like, oh well, if it's like 0.7, yep, you can round up. If it's like 0.2 or 0.1, round down. But if it's in the middle there, you might need to multiply to get the thing simplified in its most simple form. So this chemical, this would be NO or N2O3. So that's its empirical formula. Okay. So that's that first part that they were asking about. I believe that they actually asked about a second part. So let's just give ourselves a little bit more space because I love my OneNote. So we've got a molar mass of 152 grams per mole. Molar mass is 152 grams per mole. If we looked at how much the empirical formula weighed, we said, how much does that weigh? That's going to be like 2 times 14 plus 3 times 16. Is that what we did this in the last section, didn't we? That 76 grams per mole. So we knew that that was our grams per mole of this empirical formula, but we know the chemical weighs twice that. So you can say the actual chemical weighed twice that. And so the molecular formula for this chemical is going to be N4O6. And you could double check this, like you could take your 14 by 4 and add that to the 16 by 6, and that should add up to 152. But you don't really need to do that. That would just be a way to double check it. Because remember, this chemical is twice as big as that. Its molar mass would be twice as big as well. So that's kind of like the idea on these problems. And we're getting closer to the end here. Don't worry, we're almost there. So if we have something like, oh, this problem I made super easy on purpose. Let's say that you've got sample that weighs 40 grams, and you can tell it's 12 grams carbon, 2 grams hydrogen, and 16 grams of oxygen. You can already see the ratio here just from their molar masses. So if I have 12 grams carbon, yes, you can figure it out, but this is 1 mole of carbon, and I also gave like the 2 grams of hydrogen, but each one of those is only gonna have about 1 gram per mole. So this is gonna end up being the 2 moles of the hydrogen, and then the 16 grams oxygen ends up being 1 mole of oxygen as well, using its molar mass, right? Something like that. So you've got that 1:2 to 1 ratio. So we can take that information, we can say the empirical formula, the ratio between these things is going to be C1H2O1, which we write like that. But then we could say, how much does that weigh? Well, it's 12 plus 2 plus 16. And that looks to be, what, 30? Yep. And then this probably at this point looks a little bit familiar because we've already done this problem. This is that what we did earlier with the 180. This is the glucose, the C6H12O6. You see it's like the 30 right there, 180 for its molar mass. So this is just a slightly different scenario. And instead of giving you just the ratio of atoms, I gave you grams, right? But we can see that the molecular formula is the C6H12O6, like we saw with that problem up above, having that molar mass of 180 grams per mole. So that would be how you think about these problems. And then I also wanted you to see like, hey, you could do the same thing here, and it's like the exact same math, but now the sample's smaller, but we still have the same ratio. So instead of 12, 6, instead of 1, this is 0.5 or a half. And then I think this is 1 and 8. Um, uh, is that not correct? Let me just double check that. Okay, so there was a small error that I had made earlier. Instead of 40 grams, I'd meant to put 30 grams here, and this should be a total of 15 grams here as well. 12 and 16 and 2, when you add those up, you get 30, not 40. That was my mistake. You probably didn't even realize it, huh? So in any case, we've got the 6 and the 1 and the 8. We add those up, we get 15 total grams here. So we've got half the sample size, but it's still the same ratio of things. And you can see that we've just cut all of our numbers in half. And so you can consider this to be the like 0.5 to 1 to 0.5, but that's the same as a 1 to 2 to 1 ratio. So we could write it out like this, and we can work with samples of any size, any percentage, and it works out just the same as if we were doing that. We just kind of make it proportional. And that's kind of what we're doing when we're simplifying to make it a simple number to work with. Okay, I think that's it. So this is a really good example of a real world scenario where you would actually use an empirical formula and molecular formula. So there's some sample here that we don't know how many carbons, hydrogens, and oxygens are in the formula, but we know it's made up of those things. And there's some water or oxygen that's flowing over it, and it's going to react, it's going to burn. And so there's going to be whatever this is plus O2, and then it's going to be making some carbon dioxide and some water, right? The problem is that because oxygen's coming in over here, we can't determine the amount of oxygen in the products to be solely from this reactant because it's got this excess. But we can do that with the carbon and the hydrogen. So you can say like the amount of carbon dioxide that's being produced is determined by how much carbon is there. The amount of hydrogen that's being produced is determined by how much hydrogen is here because it's the only source, right? So there's some absorbers that are absorbing the mass. So whatever CO2 that was produced from here is now getting absorbed in here. And whatever water vapor is being produced here as that burns is going to get collected over here because the air is kind of getting flowed through here like that. So we have, in theory, all of the mass, all of the water's mass is being absorbed, all of the carbon dioxide mass is being absorbed. We should be able to figure out how much carbon and hydrogen we originally had, and they gave us the total mass, so we know the mass of the total sample. So there's a number of things that you can kind of start to do here. We want to know the moles of carbon, hydrogen, and oxygen. So the first thing is asking how many moles of those do we have? And you can do that with a little bit of stoichiometry. With the carbon dioxide, you can say this amount of carbon dioxide is going to relate to this amount of carbon, that amount of moles of carbon. You can do the same thing with the hydrogen. You can say, okay, I've got this much water. How much hydrogen would produce that? Unfortunately, we can't really do that with oxygen because it's coming from that excess gas. So I had done some stoichiometry here, but that doesn't work there for that. So, but if we have the mass of carbon and hydrogen, the total mass, we should be able to equate it. Because if we have, like part 1 plus part 2 plus part 3, and we add that all up, that's going to be the total. So if we know 2 of the parts and the total, we should be able to solve for that third missing piece. So we can take the moles of these things that we've got and think about how much mass or weight of carbon we have. Same thing with the hydrogen. And we know that the total mass was the 7.89 from the mass of the flask that they gave us earlier. So we've got the total, we've got our different masses of these things, and from that we can figure out the mass of oxygen. Then, on top of that, we can figure out from the mass of the oxygen how many moles of oxygen we had. And now we have the moles of carbon, moles of hydrogen, and the moles of oxygen that were originally in the chemical. You can see these are not whole numbers, so we had to do some multiplication to make them be whole numbers. I think that if you try and make like this be 1, then that ends up being 2. Yeah, and this ends up being 6. If you end up turning those into whole numbers, if you divide by 0.17 for each one of these things. So we get a empirical formula of C2H6O. And if they give us the molar mass, like right here, let's say that they've told us the molar mass is 46 AMUs or Daltons. Those are just like the very small units, kind of like the grams per mole. Grams per mole is talking about bigger system, but 46 AMU is the same as a gram per mole, 46 grams per mole. So we can see if we actually just add up their molar masses, we've got 12 times 2 plus 6 plus another 16, that is 46. So if we know that this thing has a molar mass of 46, then we can say that this is the molecular formula as well. And so we've determined for this chemical that it had both the same empirical and molecular formula. Okay, so that's the real world example. I know there's a lot of math in there. I would encourage you to try and do some of it, but that's kind of where we would actually get these things from. We actually figure out masses from experiments. Molar mass is something that if you run it through a tube, you can see how fast it goes through the tube. Things that are smaller will go through that tube faster. So you can find out how fast things are moving through the tube and determine its molar mass. And that's oftentimes a way that we will figure out how these things that have the same empirical formula, how we know which one we are actually dealing with, like what molecule are we actually dealing with, is by looking at how fast they go through these spectral analysis. Okay. All right. That's everything. Thank you for joining me. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about. And remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia. And if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm gonna be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.